Recording. Okay, it started. Okay, so we want to find the area of this, but we can't do it just by multiplying length by width because it's not a rectangle. The thing about rectangles is they have both a fixed width and a fixed height. So, and I don't have that here. I have several different heights. So what you want to do is, what we're going to start off by doing is finding the area by approximating it with rectangles. That's obviously not where we're going to end up. The whole point of calculus is we're going to be able to find the exact area, but we get there by starting off with what the approximate area looks like. So what I would do is I'd take this interval AB, because I'm only interested in the area that's above the x-axis but below the curve over the interval AB, and I'm going to subdivide it into a couple of different what are called subintervals. So okay, so these are subintervals in the sense that that they're less than the full interval, but they're still intervals. And what I'm going to do is for each of these subintervals, I'm going to pick a representative point that's going to be used for the height of a particular rectangle. So here, the first subinterval, I'm going to pick the endpoint, the right endpoint. The second subinterval, its right endpoint. For the third subinterval, I'll pick its right endpoint, and for the fourth subinterval, I'll pick its right endpoint. And what that allows me to do is I'm going to find the area of these four rectangles. Let's see if I can shade these in properly. So what I would do is I would find the area of these rectangles, and that would give me the approximate area under the curve y equals f of x. It's certainly it's not going to be the exact area, but it's a decent approximation. So a couple of things to note about the details of what I've done here. First thing is each of these points that defines the end, the beginning and end of the subintervals gets a name. What we do is we rename A. What do I want to use for this? This one. A gets the name x0. And since I'm creating four subintervals, B gets the name x4. I'm not saying we're always going to use four subintervals, but because we did, we're going to call the last point x4, and then I give these the names x1, x2, and x3. So the four subintervals can be described as x0, x1, x1, x2, x2, x3, and x3, x4. Okay, so those are the four subintervals. The other thing to note is that because I've divided the original interval equally, I can say exactly what the length of these subintervals is. Now, strictly speaking, I could get an approximation if I didn't divide the intervals equally, but for the purpose of this class, we're always going to assume that we divide the intervals up equally. We're not going to do problems unless, of course, sapling sneaks one in there, but I don't think it does. If it does, I'm going to try to take it out. We're going to assume that all of these subintervals have equal length, which means that I can actually give that a name, and the name of that length is delta x, and delta x is just equal to the length of the original interval, which is b minus a, because remember, those are x values. So b minus a gives me the length of the original interval, and I can divide it by 4. because there are four, since there are four subintervals. So what that means is that I can easily find the area of each of these rectangles in kind of a regular way. I can say that the area of the first rectangle is just going to be the height of the rectangle. Note that this point is x1 f of x1. So it's going to be the height of the first rectangle, which is f of x1, times its width, which is delta x. And the second rectangle, since this point here is x2, f of x2, you can see that the height of that rectangle is going to be f of x2, and its width is delta x, and so on for the other rectangles. So that gives me the areas of all four rectangles, and I can simply add them up. So we refer to this method of finding the area, or the approximate area, as the nth right endpoint approximation. What is the n? So n is equal to the number of subintervals, or in this example, it's certainly not required to be 4. It's just that 4 is a convenient number to draw. And we call it the right endpoint approximation, specifically because I'm choosing the height of the rectangle by picking the right endpoint of each subinterval. In other words, I pick that one for the first subinterval, that one for the second, that one for the third, and that one for the fourth. I don't have to pick the right endpoint. I could pick any point in the interval or on the end of the interval. But normally, the most common way to do this is to pick the right endpoint. If I were to use the left endpoint or the midpoint, then the names for these would be the nth left endpoint approximation or the nth midpoint approximation. I'll just show in a minute what those look like. So any questions so far about what I've done at this point? Okay, so the question is this Riemann sums? The answer is this is on the way to developing what a Riemann sum is. I realize that some of you have already seen this approximation method, and you know the formula or the method of actually finding the exact area. We're going through it in detail because I think what a lot of sort of basic high school classes in calculus do is they give you the formula without developing it. We are actually going to do problems that involve finding these approximations and showing how they get to the exact area. So next question was, will there be a specific question asking us to use left or midpoint rather than right? The answer is yes. There are questions that will ask for left and right, and I'll do one that finds the approximate area by all three for the same function in a minute. Next question is, how did I find delta x? Delta x comes from this, that if I have 2 points here, A and B, the distance between them is just B minus A. So if I divide that into fourths, then each delta x is going to be the length of the entire interval divided by the number into which I divided it. In this case, I divided it into 4, so I divide by 4. But in the more general case, if I divided it into n subintervals, I would divide b minus a by n. Okay. There's a space in front of the interval. Oh, yeah. So what you're saying is that I don't count, I'm not counting this space here, right? So yeah, that's right. So I'm only interested in the most general case. I'm interested in the area under the curve on any interval, not necessarily one beginning with zero. In fact, you can start the interval at a negative number. So the length of the interval, no matter what numbers I pick, is always going to be, b minus a, where b is the right endpoint and a is the left endpoint. Okay. So let me just go to, I just want to draw the same picture with left and midpoint approximations. So instead, I have something like this, like that's A and that's B. Once again, we'll put in, this is x0, x1, x2, x3, and x4. And I realize that one of these doesn't look like it's the same length, so you'll have to imagine that these are all the same length as each other. But here, if I draw the endpoints like that, then what I get instead are these rectangles. There we go. So these are four different approximating rectangles, but if you notice, and hopefully I tried to draw the function in the same way, if you notice, they're different heights for what's basically the same. I think I've drawn the curve pretty much the same. So it's the same function, but I'm getting different heights for the rectangles because I'm picking a different point as the basis for the height. So in this case, what I've done is, this is going to be x0, f of x0. This is going to be x1, f of x1, etc. Here I've got, I'll put them all in, x2, f of x2, x3, f of x3. And if you notice, in the last drawing, I had used f of x4 as the basis for one of the rectangles, but I hadn't used f of x0. So this just shifts everything down by one. And so what I have now is I'm going to have the four rectangles will be the area of the entire thing. Once again, putting this in as delta x is going to be f of x0 delta x plus f of x1 delta x plus f of x2 delta x plus f of x3 delta x is going to give me the area, or the approximate area. It's not the exact area. And finally, let me just draw this one more time with the midpoint. If I use the midpoint approximation, I have to do something a little bit different, because as I divide it here, although this is x0, x1, x2, x3, and x4, I can't actually use those points. What I have to do instead is pick the midpoint of each interval, where these get the name C1, C2, C3, and C4. Now, where are these points? Well, C1 is right in the middle between x0 and x1. So C1 is equal to x0 plus x1 over 2. In other words, it's just the average of the two endpoints that define its subinterval. So C2 is going to be x1 plus x2 over 2. So you see how C1 is the average of these 2 points, and C2 is the average instead of these 2 points, like that, and so on. So now what I'd get if I draw these, if I draw this approximation, I'm going to put the heights of the rectangles here, and that's going to look, I'll just quickly shade these in without having to use the highlighter. And it's going to look like that. So you might notice, some people observed last night, they said, well, isn't it the case that the midpoint approximation is just the average of the left and right approximations? And the answer to that is no. Another person said, well, isn't the midpoint approximation more accurate than the left and right approximations? And the answer to that is also no. Or I should qualify that and say it actually depends on the function. If I draw, let's say, this function, draw a function that looks like this. What you can see is that the midpoint approximation, because those are the midpoints, is going to way overestimate the area. Whereas the two, if I use, I'll just draw in the left and right endpoints here. If I use the left and right endpoints, I'm going to way underestimate the area, but the two left and right endpoint approximations in this example would come out exactly the same as each other, because, or at least the way I've drawn it is intending to make these green points the same height. So if that's A and that's B, if I'm choosing the left endpoint approximation, I choose these 4 points. And if I choose the right endpoint approximation, I choose these 4 points, and it's going to come out to the same number. The midpoint is going to be totally different and is going to be much larger than either of the left or right endpoint approximations, because I'd get rectangles that are all the way up there like that, whereas both of the left and right endpoint approximations are going to give me rectangles that high. So you can't really generalize and say, is the midpoint approximation better than the left or right endpoint approximation? It really depends on the function. For functions that look sort of typical, the midpoint approximation usually works better, but that's not universally true. Okay, so any questions now about what the approximation methods that we're using are? Okay, good. So let's see. Okay, so let's, oh, sorry, I just wanted to give you one more bit of terminology. I forgot to put this in last night also. We use the term Rn to mean the nth right endpoint approximation of f on the interval AB. So just to be clear about what this terminology means, the R means that this is going to be a right endpoint approximation. The N means that we're going to divide the original interval into N subintervals. And the thing that's not stated but is always implied is that we're talking about a specific function f and a specific interval AB. It doesn't make sense to talk about what's the area under f if f goes on forever in either direction. What we want to do is talk about the area of f on a specific interval AB like that. That's the only way that we can really talk about area. So I need a specific function f and I need a specific interval AB that doesn't make it into the notation but is always implied. Ln means the nth left endpoint approximation of f on AB, and Mn means the nth midpoint approximation of f on AB. So our book uses those notations for the right, left, and midpoint approximations. So with that said, we'll see how the notation's used and also see how to solve the problem at the same time. So let's find the right, right, left, and midpoint. I think I was just going to do a right one, and I forgot to update the slide when I decided to do them all at the same time. So let's calculate R6, L6, and M6 for the function f of x equals 1 over x on the interval 2, 4. So just to be clear, what we're being asked for are the right, left, and midpoint approximations using 6 subintervals of the original interval. So here's the drawing. This is the function y equals 1 over x. And I'm not going to draw it to scale, but let's put that in as 2. And that's 4. So what we want to do is find that area. And we need to divide it into 6 subintervals. So I've now divided it into 2 subintervals. I need to divide it into 6. So I'm going to divide the region between each integer into thirds. So this is 2. That's going to be 7 thirds, 8 thirds, 10 thirds, and 11 thirds. In other words, I'm just going a third of the way in between each integer. We can do this analytically. Let's just put in the names for these that we've been using. 2 is A and 4 is B. Those are the ends of the interval. It's also the case, in fact, I'm going to, just so that they end up lined up, let's put the A down here, the B down here. This is also going to be x0, x1, x2, x3, x4, x5, and x6. It's also the case that the distance between any 2 of those points is delta x, where delta x is the length of the interval, b minus a over n, which equals 1/3. So each subinterval has a width of 1/3. So every rectangle we draw is going to be 1/3. Is going to be 1/3 in width. So let me just draw here what the right endpoint approximation looks like. The right endpoint approximation is going to look like this. I'll keep going. I just don't want to clutter the drawing too much, but that's basically what it's going to look like, where I'm finding that area, that area, that area, and so on. So that R6 is going to equal 1/3 times 1 over 7 thirds. Now, where is this coming from? That's the width of each that's the width of the first rectangle. And this is its height, because the height is going to equal 7 thirds comma f of 7 f of x, f of 7/3, where f of x, which is y, is 1 over x. So I'm just plugging in the I'm plugging in x1 into the function. Since it's the reciprocal function, that gives me 1 over 7/3. So that's the first rectangle. Here we have 1/3. The second rectangle is still going to have a width of 1/3, but I'm using this point here and plugging that, the 8/3, into the function, giving me 1 over 8/3. So once again, that's the fixed width, which equals delta x. And this is f of x2. I should call this, let me want to be clear about what I'm doing. Okay, so that's where those numbers are coming from, is the first one is the width and the second one is the height. So I just keep going. It's going to be 1/3. I get to x3, which is 1, which is 3. So f of 3. And I do the fourth rectangle. And the fifth rectangle. And finally, the sixth rectangle. Okay, so anyone have any question about what I've done here, about how I've created this sum of 6 different things? Why is it 1 over the fraction? Because that's the function. The function that I'm trying to find the area under is 1 over x. So I'm just plugging in the x values. Okay, good. So Eric's question is resolved. Thank you, Julian. And Malia, so how did I get the subintervals? Well, remember, the original interval that I was given was 2/4, and the text of the problem says to divide it into 6 subintervals. So I'm just taking the full length of the subinterval here, which is the length of the interval that ranges from 2 to 4 is just going to be 4 minus 2, or 2. And I'm dividing it into 6 subintervals. So I get 2/6 or 1/3 as the width of the subinterval. So what I do is I just start at one endpoint and just keep going 1/3 to the right until I've filled up the entire interval. Does that make sense? Okay. So anyway, I don't want to do the arithmetic here, but if you add all this up, what you get is approximately 0.0653 as the full area under the curve on the interval 2, 4. So the area, once again, that we just found, or we found a good approximation of, was this area. So the yellow area is what that number approximates. Are there any units? Not really. This is math, not physics. I don't stress about the units as much as I know a lot of math teachers really stress about that. When we were solving word problems, yes, I definitely want you to know what the units are. When we were doing those problems where I was saying, like, what is the derivative measuring? I had megafonzies per century or something like that. Then yes, I want you to understand that as part of the problem. but this is pure abstraction. You just say units. I mean, honestly, for me, you can say units squared, and that's totally fine with me. If I'm asking for an area in a problem that doesn't have any word problem aspect to it, I'm fine with just the number. And I'm pretty sure that Sapling is asking for the same thing. I don't think they give it to you in inches or meters. I think they just say find the area, and it's a number. Okay. All right, so that's the right endpoint approximation. Now, if instead I want to find the left endpoint approximation, L6, so that's going to be the same thing. So what I'm going to do is not the same thing exactly, but what I'm going to do is I'm going to pick that point, that point, that point, that point, that point, and that point. So I'm going to use the first point, 2, but I'm not going to use the 4 at the end. So it's going to be basically the same calculation, except that this is not going to be there, and there is going to be a different one at the beginning. So we can set that up. I'm going to do this one more in the abstract. So this is going to be f of x0. I'll do it in the same order I did it before. It's going to be delta x, the width, times f of x0 plus delta x times f of x1 plus delta x times f of x2 plus delta x times f of x3 plus delta x times f of x4 plus delta x times f of x5. So in other words, I'm picking only this number, this number, this number, this number, this number, and this number, but I'm omitting the right endpoints. So this comes out to, this is 1/3 times 1/2. And some of you, by the way, may have observed that I could just pull out the delta x and put parentheses around everything else. And we will do that a little bit later. But for now, I'm just writing it out the long way. Sorry, that's not 1/2. Sorry, delta x times, oh yeah, actually it was 1/2 plus 1/3 times 1/7/3 plus 1/3 times 1/8/3 plus 1/3 times 1/3 plus 1/3 times 1/10/3 plus 1/3 times 1/11/3. So I'll answer that question. There's a question pending, and I'll answer it in a minute. Okay, so this comes out to 0.737, or I should say, actually, I want to point something out. These should both be, actually, I wrote it as an approximation sign. These should both be equal signs. The area is approximate, but these are the exact values of R6 and L6. So, okay, so we get two slightly different approximations for the same area because we're using different endpoints. If you notice, all of the rectangles for the right endpoint approximation were actually smaller. They actually omitted some of the height. You can see that like the height on top always gets omitted, whereas if I draw the rectangle up here, I'm actually including too much height. Okay, let me get back to Julian's question. Can approximation only be done when endpoints are defined? Yes, that's true. I mean, first of all, we need an interval that has endpoints in order to approximate, in order to even talk about what the area is that we're approximating. So, you know, it wouldn't make sense at this point yet. When you get to Calc 2, we'll be able to find areas under intervals that are like 2 to infinity. But for now, we're only talking about areas where there's a clear left and right endpoint to the interval. But yes, in order to come up with an approximation, you need to say what the endpoints of the subintervals are also, although it's usually defined in some regular way. We just start at the left endpoint and just keep kicking to the right by an amount of delta x. Just wait for one more question. You multiply the fractions for each there's a pattern at each interval. Does that have any meaning? Yes, you mean like that the denominator in the height is just like in the case of L6, it's 1/6/3, 1/7/3, 1/8/3. So I assume that's what you mean. Yes, that does have a meaning, and that's actually going to allow us to find this in a more principled way very soon, and it's also going to allow us to find the exact area. So I'll get there hopefully. Although I lost some time at the beginning of this lecture with the pen issue, hopefully I'll get there by the end of the lecture anyway. So, okay. So we now want to find the midpoint approximation. I'm not going to redraw the picture, I'll just redraw the number line. So if I have 2 and 4, once again, I'll put in the 6 dividing points. So this was 7/3, 8/3, that's 3, 9/3, 10/3, 11/3, and the 4 was 12/3. So, okay, so that's A and that's B. What I need in order to do the midpoint approximation is I actually need the midpoints of these intervals, which are there. Should have used a more contrasting color. So in between, notice that this was 2 is 6/3. So each of these points is just going to be the average of the two endpoints on the end of the subinterval. So if I have the average of 6/3 and 7/3, that's going to be 6/3 plus 7/3 is 13/3, and then I divide by 2 to get the average. So that's going to be 13/6. The average of 7/3 and 8/3 is 15/6. 17/6, 19/6, 21/6, and 23/6. So that gives me the midpoints. These are the center points: C1, C2, C3, C4, C5, and C6. I think it's easier to sort of just understand the geometry of where they come from rather than worry about what their names are. So in this case, we have is M6 is equal to 1/3 times 1/13/6. Once again, I'm just plugging in. This is delta x, and this is f of C1. So I'm just plugging in the center points into the original function, which is y equals 1/x. So that gives us 1/3, 1/15/6, 1/3, 1/17/6, 1/3, 1/19/6, plus 1/3, 1/21/6, plus 1/3, 1/23/26. And that comes out to 0.692. So I've got 3 different approximations. The midpoint approximation turns out to be in the middle. That is actually the most accurate approximation. It's still not exact, but it's, like I had showed before, it's not a foregone conclusion that the midpoint is always going to give the most accurate approximation. It's just that since this is a function that goes from high on one endpoint to low on another, the midpoint is actually going to give you a rectangle. It's about in the middle, but that's specific to the shape of this function. It's not something that's going to happen with every function. Okay, so any question about those approximations? Okay, so like I said, the most accurate one depends on the function. In this specific case, the midpoint one is actually the most accurate. The reason is that the midpoint is actually giving you a height for the rectangle that's between the highest point on the left and the lowest point on the right. That's due to the fact that the function is decreasing throughout the entire interval. So it's always the case that the left endpoint is higher than the right endpoint. But if you had a function that was sort of crazy like the one I drew on the other slide, that's not necessarily going to be the case. But in this case, yes, the midpoint is the closest approximation. Yeah, I mean that's sort of that's one of those conceptual questions that you might see on Sapling or a workshop problem or something like that. I mean, for exams, I would think that you'd be more likely just to be asked for, what's the left endpoint, what are the left and right endpoint approximations with some value of n. How can you tell which one is the most accurate? That really depends on an analysis of the function. So let me think. How would I describe that exactly? So in this case, it's actually going to turn out that the right endpoint approximation is more accurate than the left endpoint approximation. Let me just show you how you know that. I'm going to draw really freakishly big the shape of this function like that. So let me just draw one of the subintervals right here. Because the function is bowed down, or as we now know, the term for that is concave down, let me draw the left endpoint approximation there and the right endpoint approximation here. So if you look at what's going on, that's the amount of area that the right endpoint approximation omits. In other words, that's part of the area we're trying to find, what I've drawn in stripes, but the right endpoint approximation, the red rectangle, is missing that area. On the other hand, up here, I'll draw in yellow highlighter, that's the amount of extra area that the left endpoint approximation puts in. And as you can see, the left endpoint approximation is giving you much more extra area than the right endpoint approximation is taking away. That's due to the fact that the function is concave down. In other words, that it's concave up. In other words, concave up meaning that its derivative is increasing. But by the way, it was something that most people missed on this week's quiz, is that a concave up function has an increasing f prime. So that's one way that you can tell. But basically, what I'm saying is you really just have to look at the shape of the function and figure it out. This is sort of an advanced conceptual topic. It's not the thing that I want you to worry about the most. But it's certainly reasonable to look at a function, try to figure out which is the better estimate, and this is one way to do that analysis. Okay. Okay. So I want to go on because we have to get to a couple of notational issues in order to get to the generalization of this. Many of you have seen this, I think, in pre-calc. Anyone recognize the sigma as something called summation notation? Okay, good. So in the most general form, what we have is we have some index variable, which I'm calling k. Sometimes it's called I. I think sometimes our book sort of mixes whether it uses J and K. I use K because j gets overused sometimes. So, and then later on in the book, it switches to n being the index variable. I don't know why, but anyway. So k is the index, which really just cycles through the integers, starting at a low point of m and a high point of n. So if I have numbers like this, like am plus 1, with indices, subscripts going all the way up to n, and I want to add up all those numbers, I can write their sum in this form. As you see, if I take on the right side of this equal sign, am plus 1 plus dot, 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 all the way up to an, I can just write it as the sum from k equals m to n of ak. So, more specific example of that is, so k is the maximum number. No, m is the maximum. Sorry, n is the maximum number. K is the index variable. It's just the number that keeps cycling through. I'll show you in a minute how that just how I think of this, but here's a more specific example. And the second thing I've written is if I actually have three numbers here, I'm going to say A1 is the number 6, A2 is the number 14, and A3 is the number -5. Then I can add up those three numbers by writing sigma, the sum, from k equals 1 up to 3. So k is going to range from 1 up to 3, and it's going to go through all the integers in between. And that is going to equal A1 plus A2 plus A3. So in other words, here, note that this is k equals 1. This corresponds to k equals 2. This corresponds to k equals 3. And what I'm doing is in the expression that appears after the sigma, every place I see a k, I'm going to replace it with a specific value of k as I cycle through all the possible integers going from 1 up to 3. So here I replace the k with 1, giving me A1. Here I did the same, got A2, A3. And then finally, since I've assigned specific values to these numbers, I can then just replace them with the numbers. That's A1, that's A2, that's A3. I add them together and I get 15. Typically, instead of being given just some arbitrary list of numbers like A1, A2, and A3, we have an expression. So here, just to clarify what we're doing, the sum from k equals 2 to 6 of k is going to equal, I'm going from k equals 2 to 6, so I'm going to put in k equals 2, k equals 3, k equals 4, k equals 5, and k equals 6. And then in each of those, what I want to do is replace the expression after the sigma, which is just k itself, with the value of k. So this expression just means add up the integers from 2 to 6. I replace k with 2, I replace it with 3, 4, 5, and 6, and that gives me 20. Okay. So any questions about how that notation is used? All right. Let's go on. So these rules apply to summations, and these I don't want to dwell on them because they're actually pretty similar to the rules we already know for limits and derivatives. All this means, for example, is that, let me just put up an example here. If I want to find the sum from k equals 1 to 3 of k squared plus k, that's going to equal the sum from k equals 1 to 3 of k squared plus the sum from k equals 1 to 3 of k. I'm sorry, Eric asked, what is the k equals m determinant? And the answer is yes. M is the starting number. It's the lowest number. Okay, so this is going to equal sum from k equals 1 to 3 of k squared is just going to, remember, I'm cycling through the integers from 1 to 3. So that's going to be 1 squared plus 2 squared plus 3 squared. And then I'm going to cycle through the numbers 1 to 3 again. That gives me 1 plus 2 plus 3. And if I add all those up, that comes out to 1 plus 4 plus 9 plus 1 plus 2 plus 3, which is 19. And that's the same answer that I would have gotten if instead I had simply evaluated this directly. If I instead I hadn't broken it up into the two summations and I had just treated the expression as k squared plus k, then I'd get 1 squared plus 1, 2 squared plus 2, 3 squared plus 3, and I'd get the same number, 19, because as you can see, I'm just adding up the same 6 numbers in a different order. So you can think of this as really just kind of the commutative property for summations. What this one means is I can pull a factor out. So what that means is, for example, the sum from k equals 10 to 12 of 2k is equal to 2 times the sum from k equals 10 to 12 of k. It sort of makes sense because what that means is that 20 plus 22 plus 24 should equal 2 times 10 plus 11 plus 12. It just means that. And then finally, we have this sort of case that many people miss, which is that if I take the sum from k equals 1 to n of a constant, c is a constant, and I add it up, I'm just adding the constant to itself n times. So just for example, k equals 1 to 5 of 3 is equal to I want to write these in so it's clear what I'm doing. So these are the k equals 1, 2, 3, 4, and 5 terms. Here's the expression after the sigma. Every place I see a k, I replace it with the value of k, but k doesn't appear anywhere in the expression, so there's nothing to replace, and I just get 3 plus 3 plus 3 plus 3 plus 3, which is 5 times 3, or 15. So that's what this expression means. Okay. All right, so any questions about that? Okay. So let's okay. There are a couple of special rules for summations that you have to know, these are just formulas that are actually going to be very useful as we use these to find areas, as we use summations to find areas, which I'll show you in a minute. So the first one is that if I add up the first k integers starting at 1, the first capital N integers starting at 1, their sum is n plus 1 over 2. So just for example, sum from k equals 1 to 5 of k, which is 1 plus 2 plus 3 plus 4 plus 5, is equal to 5 plus 1 over 2, which is 30 over 2, or 15. So when you're just adding up 5 integers, this is not all that important. But if instead I had the sum from k equals 1 to 100 of k, if I wanted to add up the first if I wanted to add up the first 100 integers, so that's 1 plus 2 plus dot, 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 plus 100, that's going to be 100 times 100 plus 1 over 2. So that's going to be 10100 over 2, which equals 50/50. So you can see why it's sort of useful to have a formula for that, because, although you could add up 5 integers, adding up 100 integers is not as easy unless you have a computer. So how are these formulas? These formulas are demonstrated by a process called mathematical induction that I don't really want to get into. So so they're just constants. These are just formulas for adding up the first k numbers, the first k squares, and the first k cubes. So I'll just do an example of the second one. So that comes out to the sum from k equals 1, let's say, sum from k equals 1 to 3 of k squared, which is 1 plus 2 squared is 4, 3 squared is 9. That's going to equal 3 times 3 plus 1 times 2 times 3 is 6 plus 1, which is 7 over 6. So that's 3 times 4 times 7 over 6, or 84 over 6, which is 14. And if you actually add up 1 plus 4 plus 9, you'll see that you do, in fact, get 14. So, this formula does work. Yeah, that's it. They're useful for higher n values, and as we're going to see, they're also useful. As we're going to see by the end of this class, they're also useful for infinite n values, and that's really the point of doing this. So let me show you what the use of these is. I just need to go through one more theorem and definition before we can get to that. So what we're going to do is we're going to talk about area as the limit of a sum. So this is the relevant theorem, is if f is continuous on AB, then these three expressions are equal to the same number. I'll show you what they mean in a minute. And as long as f is greater than or equal to 0, we can actually define this number, this limit L, as the area under the graph of f on AB. So what do I mean by that? What does all of this mean? Suppose that I have this function here, and I look at R3. So in other words, I've taken those three rectangles as the approximation of the area under the curve. As you can see, this is not going to be a very good approximation because it goes under and over the curve. The rectangles, the first rectangle is omitting quite a bit of area like that. The second rectangle is including a little too much area. So these are not going to be really good approximations, but it is an approximation. If I wanted to do a better approximation, what I might do for, I hope I'll draw as the same function, is maybe what I'll do is instead of R3, maybe I'll draw R100. So obviously I'm not going to draw in all 100 rectangles, but the point is that you can see that if I did this, I would get an even better approximation I get an even better approximation of the area, because each rectangle's height is going to be much closer to the small amount of movement that's happened, the small amount of vertical movement that's happening in a much shorter interval. So if R3 gives a good approximation, R100 gives a better approximation. So the question is, what happens if I instead find R infinity, where I take an infinite number of rectangles, but I make them infinitely skinny. So I'm adding up an infinite number of rectangles whose width is 0. Well, you can sort of see that's not going to work, because what I'm doing is I'm adding up a whole bunch of expressions that look like 0 times infinity. Or sorry, that look like, or rather, I'm adding up infinity times 0 times f of x1 plus 0 times f of x2 plus dot, dot, dot. And as we've seen, 0 times infinity is actually an indeterminate form that we had to solve with L'Hopital's rule. We're not actually going to have to use L'Hopital's rule in this case. The point is, you can't just say, well, there's a 0, so it's 0, because you could also just say, well, there's infinity also in the product, so you really don't know which one it is. So the point is that if I use an infinite number of rectangles, I'm going to get the exact, not a good approximation of the area, but an exact area. And I'm going to need limits in order to add that up. What the theorem is saying is that once I make these rectangles infinitely skinny, and I put an infinite number of them, it doesn't matter whether I'm choosing the right endpoint, the midpoint, or the left endpoint. I'm going to get the same number. And that number is going to be the exact area under the curve. So this is how we are actually going to define area. It's not the final way that we're going to use to find the area, because there's a theorem that's going to let us do this much more easily. But this is where we're going. This is where I've been going with this approximation, is that the exact area under the curve comes from finding the approximate area under the curve, but letting the number of rectangles become infinite. So let's do that in a situation where we already know what the answer is. And hopefully you'll see how this works and how this all comes together with the sums. So let's find the area under the graph of f of x equals x on the interval 0, 4, using the limit of the, I'm just going to use the right endpoint approximation, just because I don't want to spend a lot of time doing the other one. Maybe we'll do the other one next time. So here's the function f of x equals x. And there's the interval 0, 4. Okay. If I wanted to do 4 rectangles, what I'd get is an approximation that looks more or less like this, which, as we've seen, is kind of problematic because it just includes too much area. There we go, like that. So that's not going to be a very good approximation, but let's see what would happen if instead I let it be infinite rectangles. Well, I get the exact area. Well, first of all, what is the exact area? This is just a right triangle. The area under this curve is just a right triangle with a width of 4 and an altitude of 4, a base of 4 and an altitude of 4. So that's just going to be 1/2 times 4 times 4, which is 8. So that's the exact area. Let's see what happens if we use this approximating method with rectangles and to see if we get the same area. Okay. So first of all, let's calculate Rn. Let's find an expression for Rn, rather. So instead of finding, like, say, R4, I just want to find an expression for Rn. Well, first of all, let's find delta x. Delta x is going to be b. Remember, that's our a and that's our b. B minus a over n, which equals 4 over n. So if I choose n rectangles, then each one of them is going to have a width of 4 over n. It's also the case that if that's A and that's B, since delta x just kicks us, since x0, x1 is just going to be delta x to the right of x0. Here's x1, x2, x3, and that's x0. That means that that x1 is just going to be A, or 0, plus 4 over n. In other words, it's just going to be delta x to the right of that. x2 is going to be x1, which was 4 over n, plus another 4 over n, which equals 8 over n. x3 is going to be 8 over n plus 4 over n, equals 12 over n, etc. So you can see that in each case, x1 is 4 over n, x2 is 2 times 4 over n, x3 is 3 times 4 over n. So xk is just going to equal 4 over n times k. So look what Rn equals. So Rn, oh, and then of course, let me just write out the expression for f of xk. So f of xk is just going to equal xk, because the function itself is just f of x equals x. So that equals 4 over n times k. So Rn is going to equal delta x, which is 4 over n, times 4 over n times 1. So this is the width, and this is the height. Then it's going to be plus 4 over n, that's going to be the width of the next rectangle, times its height, 4 over n times 2. And we can keep going. But what you see is that if I keep going here, it's just going to be 4 over n times 4 over n times the highest possible value. Recall that this is going to be x1, x2, x3. This goes all the way up to xn. So 4 over n times n. If I factor out the 4 over n, because note that this term was common in every case, this is going to be 4 over n times 4 over n times 1 plus 4 over n times 2 plus dot, 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 plus 4 over n times n. And I can rewrite this actually as, let me rewrite it this way. I can actually factor out another 4 over n, so that gives me 16 over n squared, 1 plus 2 plus 3 plus dot, 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 plus n. And look at that. That comes out to 16 over n squared times the sum from k equals 1 to n of k. Using the formula on the last page, I can replace this with 16 over n squared times n plus 1 over 2. I need to copy. Oops, not what I meant to do. So I've got this expression. Sorry, I know I have to turn the page and you're going to miss seeing what's on that page, but this can be rewritten as, this is going to be 16 over 2, gives us 8, just simplifying that, times n squared plus 1 over n squared. So that's equal to Rn. We've already seen the theorem that says that the limit of Rn is going to give us the exact area. So the limit as n approaches infinity of Rn is equal to the limit as n approaches infinity of n squared plus 1 over n squared. We have, sorry, rather, limit of 8 times Rn is going to be 8 times that. So we know that we have the same powers. We use the highest powers of with the coefficients of the highest powers, and that gives us 8 times 1, which is 8. Why is it n? Oh, sorry, this is n squared plus n. There we go. Thank you. Okay, so there we go. So finding the area in this extremely roundabout way, we were able to find the same area that we knew geometrically. That we knew geometrically was the area of that triangle. Obviously, we're not going to use this to find areas that we already know. The whole point is this is going to give us the basis to find the area under something that's not a triangle or not a straight line. We'll get to that. No, I'm a minute over. We will get to that next time. Okay. By the way, as I'm looking at the time here, I realized that even though I lost what I thought was 20 minutes doing the pen, somehow I managed to have only 10 minutes missing from the lecture. And it occurs to me, I must have been so confused this morning that I thought the lecture started at 10:10. Fortunately, at 10:10, I was just doing the silly showing of my Passover pictures, so I don't think that anybody missed anything. But that's amazing how that sort of thing works out. So I apologize for that. Okay, anyway, unless anybody has any questions, I'm going to go. Don't forget, I have office hours coming up starting at 12. I'll send the WebEx link around again, but you can also find it on the homepage for Canvas.